My name is John, and today I will introduce consistency regularization in semi-supervised learning. I recently got interested in semi-supervised learning, and this is one of the main approaches in the current literature. I'll introduce two landmark examples and then close with some extensions. Firstly, why is semi-supervised learning important? Well, there are plenty of domains in which there's lots of data, but then labeling is hard. A motivating example is a 2 moons dataset, in which there are 6 labeled samples, given by the 3 black dots and the 3 white dots. Given only labeled data, this supervised model does something close to max margin, which we may expect from the current understanding of neural networks. And the human will probably draw a decision boundary similar to that supervised decision boundary. However, given the unlabeled data, it is clear that the decision boundary should lie in between the 2 half moons. And the question is, how can we utilize the unlabeled data? One method is consistency regularization. And this is particularly interesting to me because the general idea is simple yet effective. Given an input x and a neural network output f, the general idea is that the predictions for augmentations of an input should be similar. And many methods in this domain are based on the low density separation assumption that the decision boundary should lie in low density regions. This is typically achieved by adding an additional loss function similar to this form, where x is the input, data are the parameters of the neural network, and augment is a stochastic function. There are two main approaches for consistency regularization, and I'll present one landmark paper in each, in this order. So firstly is augmenting both labeled and unlabeled data. Consider this question. In the context of consistency regularization and data augmentation, what kind of augmentations cause predictions to be the most different? Well, one answer is adversarial perturbations. And even though the literature says that adversarial robustness can worsen generalization performance, it works well in semi-supervised learning on this implementation. So with adversarial perturbations, the goal is to smoothen the prediction in the direction of the adversarial perturbation. This is exactly the idea of virtual adversarial training, which is an extension of adversarial training to the semi-supervised learning domain. It perturbs inputs in a direction which changes the current inferred output distribution the most, and the pole part is what allows it to be applied on unlabeled data. This is the classic form for adversarial training for the objective function, where D is some measure of the divergence between distributions. Q is a true output distribution, and in the supervised case, people typically use a one-hot vector for the label. X star in the context of semi-supervised learning is both labeled and unlabeled data. R here is a vector, and the interpretation of R is a direction which changes the output distribution the most. For VAT, they use the KL divergence for D. So there's one problem, and that's we don't know Q, especially for unlabeled data. The authors here suggest that we use a surrogate, which is the current predicted output. And this can be problematic, but works practically. Unlike most other semi-supervised learning methods, they define an additional loss, take the mean over both labeled and unlabeled data, and add it to the existing loss with some coefficient alpha. So how do we compute R? In adversarial training, a common method is to use a linear approximation. However, note that the gradient of D with respect to R at R equals 0 is 0. This means that a linear approximation doesn't work. However, taking the second order Taylor approximation results in this form, which is approximately the rescaled first eigenvector using the 2 norm. So this is quite nice because this lets us use our familiar tools such as power iteration, which is what the authors suggest here, and they approximate the iteration to avoid computing the Hessian. Going back to the toy dataset of the 2 moons, here the first row is the output distribution, the predicted output, and gray means in between the two classes. So about predicted, the class is 0.5 if one class is 1 and one class is 0. The bottom row here is the value of the loss function, and gray means low. So you can see here that after 10 updates, it seems like the network is drawing a decision boundary similar to the supervised case. And drawing the decision boundary down the middle or through a cluster means that the output distribution changes very quickly with small perturbations. This is why the additional VAT loss function is very large. However, by minimizing the VAT loss, it very quickly pushes the boundary away from the clusters. and now you get something closer to what a human might draw. So one thing you might ask for this 2D toy example, what about random perturbations? And this works well for the 2D example for this toy data set, but for high dimensions, this does not work very well. And you can imagine that for a 300 by 300 image, an RGB image, a random perturbation is unlikely to be very meaningful in terms of the decision boundary. Now moving on, there have been significant advances in image classification in the semi-supervised learning domain by mixing labeled and unlabeled data. And instead of introducing a particular method, I'll introduce the core idea and give intuition. The core idea involves this routine, and it's the mix-up procedure. The mix-up procedure draws a lambda from a distribution that's typically wide at 0 and at 1. It takes input label pairs x1, y1, and x2, y2, and combines them via a convex combination. This works particularly well for semi-supervised learning. So why is that the case? Going back to the original motivation of this method, it was introduced to encourage linear behavior of the network between samples for supervised learning. And this was by Occam's razor. But we don't know the labels for unlabeled data. However, going back to the low density separation assumption, the decision boundary can still be encouraged to lie in low density regions as long as we have a lot of data points. So this turns out to work very well for semi-supervised learning. Going back to the toy dataset, here ICT is a method based on mix-up, and you can see that in the beginning it draws something close to the supervised case. However, the decision boundary is quickly pushed away from all data points and resides in this low density region after 1000 updates. This follows our intuition about mix-up methods. Both these methods make significant improvements over the supervised case using a wide ResNet28 model and a classic CFAR10 dataset. Before I present my thoughts on future directions, I want to motivate future work by this question. What are consistency regularization methods really doing? So one interpretation is that they are trying to do metric learning, which is essentially trying to decrease the distance in the embedding space between points of the same class. And inspired by this interpretation, I have the following thoughts. One is perhaps there is a complementary approach where we also increase the distance between data and other classes. I have some work in this area in applying semi-supervised negative sampling to semi-supervised learning. This is based on the observation that we can decompose the cross entropy into two parts, a supervised part and an unsupervised part. And in this expression, x1 is the input, y1 is the label. There are n supervised, n labeled samples, n sub u unlabeled samples, and mu here is the output of the neural network. You notice here that if you can pick those indices j well in that unsupervised part, this can be a very helpful loss function. But we don't know the true label. In practice, even a straightforward application in which we select those indices j that refer to the outputs that are below some threshold t, and this works well. In fact, we get large improvements over the state of the art by combining with these consistency regularization methods. And this further supports the idea that these methods are complementary. A second idea on extending past consistency regularization is, can we directly impose certain structure on the embedding space? And this is as opposed to this happening implicitly with consistency regularization-based approaches. This is what I think are the future directions, and this is all I have for today. Thank you for listening.